My name is Ray Nims. You've probably heard me talk before. I've given, I guess, 5 presentations during ISIA meetings in the past. And this time I decided that I would try to give you some flavor of the comparative efficacy of various barrier treatments for viral risk mitigation in human serum versus bovine serum. So you can go ahead and advance this. Are you all seeing the second slide then? Okay. Just to let you know, I'm kind of a collector of facts, and years ago I started collecting information about barrier treatments for animal serum. This is back when I was at Amgen still. And out of that came some publications, review articles that described all the different results that people over the years have collected or accumulated on the use of gamma irradiation for inactivating viruses in bovine serum. So there was a biologics review, and then later on a review that came out of the ISIA best practices in gamma irradiation. So now what I'd like to do is to expand a little bit and maybe do some comparison or some estimation, let's say, of the efficacy of gamma irradiation on human serum. So obviously, most of the data that are available now for inactivating viruses in serum have been derived from studies on fetal bovine serum. And as I mentioned, I have presented these data previously at PDA meetings and ISIA meetings and webinars. Unfortunately, there are very limited data for inactivating viruses in human serum. This will end up being kind of a theoretical talk then, but I will discuss my expectations on efficacy and, where possible, back up those expectations with actual data. Let's move. So why are barrier treatments needed for bovine or human serum? Barrier treatments are intended to mitigate, but remember, never eliminate completely, the risk of introducing a viral contaminant into a geographical region. And this is, an import concern, or of introducing a viral contaminant into a cell culture. This is what I refer to as a user or biologics industry concern. The most common barrier treatments used for serum include gamma irradiation and heat inactivation. Now, I'll go ahead and mention right now that heat inactivation originally wasn't intended to be a barrier treatment to eliminate viruses. It was intended to render complement inactive. And I have to admit, over the years, I was myself sort of skeptical about the efficacy of heat inactivation for reducing viral risk. But the more I looked at heat, the more I realized that for many viruses, even the heating that is done for inactivating complement is quite effective for inactivating viruses. And what I mean about this complement heat, that's typically 56 degrees for 30 minutes. So whenever I say heat inactivation of serum, I'm going to be talking about 56 degrees and 30 minutes. Now, these barrier treatments, both of these, display dose response efficacy curves as you would expect. What that means is At the lower doses, you get some inactivation of virus, and you can increase the dose to kill more virus. That's a given. However, we have to balance that use of higher doses against the need to preserve the performance of the serum for the cell culture application. So unfortunately, we can't just raise and raise and raise the dose of the barrier treatment to make sure we kill all of the viruses. That's not an option. Next. So what is the risk in non-barrier treated serum? Well, obviously there's a risk of viral contamination. And this simply comes because virus or serum is sold as large pools of individual serum collected from animals or humans. And so even though there are mitigation factors in place, such as geographical sourcing, this is especially true for fetal bovine serum, oversight of the abattoirs or the blood collection sites, and the testing that's required for viruses in serum pools or in the final product that you would buy. The problem with testing is, remember, these are very large lots of serum typically, and out of those large lots, typically one bottle is submitted for viral safety testing. So there's a sampling problem there, which means that even if you get a negative test, there's always a risk that some other bottle in that same batch might have some virus or detectable amount of virus. So sampling and testing is really not a great mitigator of viral risk. Hence the need for barrier treatments. And again, before we move on, I'll just say barrier treatment is simply a treatment that you apply to the product to inactivate virus that might be in there. So now we're going to finally start to compare human versus animal serum or bovine serum, let's say specifically. Are there differences in the viral risk for human versus bovine serum? Actually, the differences apply to the types of viruses of concern for the two different kinds of serum. So, animal serum in general and bovine serum in particular, the viruses of concern are dictated by regulations, USDA regulations, which were put into place to mitigate, import risk. And we'll get to the specific viruses in a minute. But for human serum, what we're talking about primarily is the risk of blood-borne viruses. And here, the FDA has guidance in place. And what you'll find is that the viruses of concern for human serum, let's say used for manufacturing purposes, the risks are pretty much borrowed from the risk associated with transfusions. So we'll get into those viruses of concern in a minute. But what I would say is that both human and bovine sera are associated with viral risk. What's a primary difference is that the viruses of concern vary. Now, when you get to the characteristics of human versus bovine serum, in other words, the matrix effects, conferred by the serum products that might impact the barrier treatments, gamma or heating, what we find is that these matrices should be similar enough that we can extrapolate data from bovine serum to human serum. And when a client asks me to do a risk assessment for a human serum product, what I have been doing primarily is using data from bovine serum uh, to address that risk and to assess the efficacy of the barrier treatments that might be used to mitigate risk. By the way, save your questions at the end of this. We'll go through and I'll answer any questions that come up. Now, this table I put into place for you to show kind of the differences in the viruses of concern for bovine versus human serum. On the left are the virus families. These are in alphabetical order. And then there's a column for the bovine serum and the human serum. And then beneath, you will see the regulations that dictate, or mandate the testing for these specific viruses of concern. For bovine serum, it's the USDA regulations, which are articulated in 9 CFR Part 113.47. It's called detection of extraneous viruses by the fluorescent antibody technique. This, if you Google this will tell you exactly what viruses need to be tested for a bovine serum or a canine serum or an ovine serum. So here we find that bovine adenoviruses are of concern. I'll skip down to the flavivirus family, BVDV. Herpes viruses aren't in the 9 CFR, but World Health Organization asks you to test for this bovine herpesvirus 1. And also the one beneath it is the shipping fever virus, or PIV3. This is coming out of this is the EMEA, the European document. The bovine parvovirus, bovine respiratory syncytial virus, bovine polyomavirus is again an EMEA virus of concern. And then reovirus, blue tongue virus, bovine rotavirus, 3 viruses from the reovirus family. Retrovirus, there's bovine leukosis virus coming out of the EMEA guidance, and rabies virus, which everybody's concerned about. So that's the primary list for adenoviruses, for bovine viruses. And I added this Schmallenberg virus up at the top. It's a bunya virus. It's an EMEA concern for serum that comes from certain geographical regions. Then you see on the human side, it's a much shorter list. And what you find again is that these are primarily viruses of transfusion concern, such as the hepatitis C, West Nile, and Zika viruses, hepatitis B virus, this parvovirus B19, hepatitis A virus, and of course, the retroviruses. I added to it emerging coronaviruses as a nod to the recent pandemic that we were faced with the SARS-CoV-2. So when you then look at the ability of a barrier treatment to inactivate viruses, the differences between bovine and human serum is we concentrate on the ability of the treatments to inactivate a different set of viruses. Okay. So again, the relevant barrier treatments for serum, gamma irradiation is done on deeply frozen serum. We'll get to the reasons why in a minute. Heat inactivation obviously is done on liquid serum. And again, this is 56 degrees at 30 minutes. Ultraviolet C irradiation is done on liquid serum. I would say currently it has rarely been used, but in preparing for this webinar, I realized there are some data out there, and I didn't want to cover it in this particular webinar until I had assembled all of the relevant data. So if desired, I may come back to this topic in a future webinar. Now, before we start to look at efficacy, let's take a look at the mechanism of action of these barrier treatments. So gamma irradiation has both direct and indirect effects. And what we want for inactivating viruses in serum is we want the direct effects. Indirect effects are indiscriminate and lead to performance issues for the serum. So how do we get the direct effects and not the indirect effects? Well, it's pretty easy. This is where the temperature comes in. In order to get the direct effect only, we need to limit the indirect effects. So we do that by irradiating serum at very low temperature, typically dry ice temperature, minus 65 to minus 80. We make use of the fact that serum has a lot of protein in it, which actually acts as scavengers to reduce the amount of indirect activity. Also, we irradiate serum in the sealed bottles so that the oxygen levels are not high. On the other hand, you can see above the indirect effects. They basically come from all these gamma photons interacting with the water and oxygen to produce reactive oxygen species that can then not only hit the genomic material that we're portraying here, but can interact with other cellular other parts of the serum, such as proteins and things that we don't want to get rid of, growth factors, let's say. So these kind of effects are more likely to appear at ambient temperature when the serum is liquid, or in the presence of few scavengers. So these would be in protein depleted solutions, and well oxygenated conditions favor the indirect effect. So again, this is why we irradiate serum at very low temperature in sealed containers. And by doing so, what we're actually doing is favoring the direct action of photons on the genomic material of the virus. Now we go to heat. That's the next slide. And this is a figure that I put in one of my papers comparing low pH and high pH effects. But it turns out that low pH and heat kind of share a similar mechanism of action. And what we find is both of these create kind of gaps in the capsid protein layer, which both envelope viruses and non-envelope viruses have. So kind of in this crude depiction, we create spaces in the capsid which allow either nucleases to enter and degrade the genomic material, or allow the genomic material just to come out into solution, leaving you with an empty capsid. Okay. Now, that mechanism sets up this slide, which discusses the dependencies for virucidal efficacy. So obviously, in any irradiation method, the fluence is what determines the amount of viral inactivation. And it's handy that for gamma irradiation, that the fluence value is in units of kilograys. This takes into account already the dose rate of the reactor, the irradiator, and the time of irradiation. So with one value, we can account for the total irradiation dose. And again, that's in kilograys. For temperature, for heat inactivation, what you have is temperature and time at temperature. So temperature is very important, but once you choose a temperature, the amount of time is the primary dependency. With heat inactivation, obviously, you get with greater temperatures or greater times, you get greater inactivation. With gamma irradiation, with greater fluence values, you get higher inactivation. And then discussing the matrix, this is the serum itself, the matrix that you're inactivating viruses in. Again, we talked about the importance of scavenging protein for gamma irradiation. We talked about oxygenation, and we talked about the temperature. Now, I will say, if your application will permit it, if you could gamma irradiate your serum at a higher temperature or in the presence of oxygen, you will kill more viruses. There's no question about that. It's just that typically you're going to have performance issues with that serum. So what we're left with is a method which maybe causes less killing of viruses, but preserves the performance of the serum. Sorry, just one before you, one more point on that slide. With heat, there are differences between heating of liquids versus heating of viruses, let's say deposited on surfaces. And also the presence of organic load impacts heat inactivation. So in our case with serum, the organic load is essentially the same as the matrix that we're talking about. The high concentrations of protein, presence of perhaps lipids, all of that comes into play to provide differences in matrix, which can impact the barrier treatment. Now we can move. So why would, let's say, why would gamma radiation or heat kill some kinds of viruses and maybe not others? Because we're going to find out that that's definitely the case. Well, the dependencies in terms of killing or inactivating viruses are different for heat and for gamma. For gamma, it's mostly the particle size. When I say particle, I mean the virus particle size. So the smaller the microbe, the more gamma irradiation you need. Whereas bigger ones, bigger viruses, or let's say small bacteria versus large bacteria, or even going all the way to human cells, the larger you go, the less of a dose you need to inactivate the microbe. But with heat, it's a little bit different. As we saw mechanistically, heat is producing gaps in the capsid protein. So the efficacy really depends more on the specific capsid makeup of the virus than anything else. And what we find with these two barrier treatments, that unlike chemical inactivation, the envelope status of the virus is not particularly important for determining efficacy. Okay, now I'm going to give you my quick prediction. Should we use the same barrier treatment for human versus bovine serum? What difference in efficacy should we expect? Well, as we discussed, the matrix effect should be very similar. Human serum is very similar to bovine serum and makeup. and protein concentrations and such components, let's say. So I wouldn't expect any differences based on matrix. Gamma efficacy, I wouldn't expect any difference there, given that similar fluence values are applied under similar conditions, mainly deeply frozen serum. Heat treatment, however, may show some differences depending on the virus of concern. And we'll see that we've got one specific case which is of great importance when we discuss human serum heat inactivation. Because there is this one virus, human parvovirus B19, which acts completely differently from animal parvoviruses, such as bovine parvovirus. And when I say differently, it turns out for whatever reason that this human parvovirus B19 is very susceptible to heat inactivation, which is certainly not the case for bovine parvovirus. Okay, this is a big one, so I'll spend a little bit of time with it. On the left again are your viruses of concern, the virus families in alphabetical order. Second column lists the bovine viruses of concern. You've seen this before. And the next column, the human viruses of concern. And now the data, and I have to say that these values shown on the right side of the table all come from gamma irradiation studies performed on bovine serum. But again, I think it's fair to extrapolate those values to the values that we would expect to see if we gamma irradiated human serum. So primarily what we're looking for here is differences in efficacy that are based on the differences in viruses of concern. And so just looking at the top, what I've given you here is an activation based on in log 10 inactivation per kilogram. And then the next column is the estimated inactivation of the virus at the low range of gamma irradiation, which is 25 kilograms. You can take, you'll all get copies of this table. Let's say that you had your serum inactivated at 35 kilograms. So you can make this calculation yourself. You multiply 35 times the amount of inactivation per kilogram. That'll give you your estimated log inactivation at 35 kilograms. So feel free to do that. You can predict what your inactivation will be at any specific irradiation value that you got from your serum irradiator. And finally, the column on the far right side tells you the specific virus that was tested for in the inactivation study for the gamma treatment. What do I want to really bring out here? Again, you can see that adenoviruses, the top 5.1 logs is pretty good in activation. Bunyavirus at between 7 and 10 is adequate in activation. Coronavirus is greater than 10, so you can see that 25 kilograms is going to mitigate coronavirus concern entirely. BVDV 5 kilograms, bovine herpes virus is 7.8, and shipping fever virus 5.2. Now you see the one in red. This is our problem child, the parvovirus, bovine parvovirus. It's just not inactivated well by gamma irradiation. And it's primarily because this is a very small virus. The next one, picornavirus, hepatitis A, adequate inactivation there. And then we got another problem here with bovine polyomavirus, it's just not inactivated well by gamma. And the next three, reovirus 3 to 4.9, retrovirus 2.8, that's a little weak, and then rhabdovirus is 8.5. So this is telling you, if you look at this extended list, there's really only two specific viruses that are not handled well by gamma irradiation, and that's the parvovirus and the polyomavirus. Okay, you can look at this at your leisure, and now we're going to go to heat. Now, I told you before that, that heat wasn't really intended to be a virus inactivation step. It just turns out that it actually is. But having said that, you can see from this list all the ones in red, which are poorly inactivated by at 56 degrees in 30 minutes. So I would say that the list of viruses which are resistant is longer for heat than it is for gamma. But you can see there's some viruses which are very adequately inactivated. Again, the coronaviruses, the flaviviruses, and paramyxoviruses. Down at the bottom, rabies virus, the rhabdovirus. Retroviruses are very easy to inactivate with heat. And human pneumovirus, or respiratory syncytial virus, very, very well inactivated. So the ones that aren't are the adenovirus, the bunyavirus, hepatitis B virus, which is a virus of human concern, and bovine herpes virus. Down at the bottom, polyomavirus and reovirus. So these are the ones that are not inactivated well by heat. And let's go to the very middle. You see the parvovirus line there. And the virus of concern for bovine serum is not at all inactivated by heat. But that parvovirus of human concern, at the same heating level, you're getting more than 10 logs of inactivation. So that's a huge difference. And you will see later, this is why I advocate the inclusion of heat inactivation for human serum, specifically to mitigate the risk of this parvovirus B19, which won't be addressed by the gamma irradiation. Okay? And again, you can just go back a second. I've indicated in some cases on the far right column where this virus has been tested specifically in serum, either bovine or human. In other cases where there's not a footnote, these were just tested in liquid with maybe small amounts of serum. That wasn't tested specifically in serum. Okay, next. So some comments and conclusions coming from these efficacy tables. Remember that the efficacy values that I showed were taken at the low end of the serum irradiation dose. Typically, the doses go from 25 to 45 kilograms, but I've shown you how you can calculate efficacy for doses other than 25. So you can go through that procedure when you get your certificate of irradiation from your irradiator. Let's say they say 33 kilograms. You can plug in, you can calculate based on the method that I showed you and see what your expected inactivation will be. Again, most of the data, or I would say all of the data shown for gamma are for irradiation in bovine serum. The two virus types that are not expected to be inactivated by gamma irradiation, even at 45 kilograms, are the polyomaviruses and parvoviruses. Now we'll talk about heat. Again, The data that I showed were at a very specific condition, the typical heat inactivation of serum at 56 degrees for 30 minutes. Depending on your application, you certainly can either raise the temperature of heating or increase the amount of time and obtain greater virus inactivation. That's always possible. For instance, pasteurization, 60 degrees for 10 hours. That's a really great way to kill viruses. It's just that these extended treatments at higher temperatures may not be compatible with performance of the serum in your application. But just keep in mind, with any of these barrier treatments, you can always push the conditions to achieve greater viral inactivation. You just have to make sure that the serum still works for you. All of the data for heating I've shown you are for heating of liquids, and in some cases, heating of human or bovine serum. This barrier treatment is not expected to be effective for polyomaviruses, parvovirus, bovine parvovirus, I'll be specific, reovirus, adenovirus, or bunyavirus. But importantly, human parvovirus B19 is very susceptible to this heat treatment. And that's an important thing to remember. Next. So in conclusion, there's no question that gamma radiation is the primary method for mitigating risk of viruses in serum. And this is echoed in the USDA and World Health Organization regulatory documents. It is not perfect, though. We have to remember that. The few remaining viruses that will survive gamma radiation are the parvoviruses and the polyomaviruses. You know, from an import point of view, these resistant viruses perhaps are not of great concern. Unfortunately, for biologics users, any virus is of great concern. The next one is for heat. Heat inactivation at 56 degrees for 30 minutes could mitigate the risk of some of the viruses of concern from the USDA, World Health Organization, and biologics manufacturing points of view. Some of the viruses that may survive this treatment are polyomaviruses, bovine parvovirus, herpes viruses, adenoviruses, reoviruses, and bunyaviruses. So quite a few viruses that could be of concern will survive this treatment. Okay, my recommendation. Again, gamma radiation is by far the best treatment. Use the highest irradiation that your application will support or be compatible with. Heat inactivation is more effective than most people think, but the list of resistant virus types is longer in the case of heat. Heat will kill human parvovirus B19, which means, because of that, if you are going to barrier treat human serum, I advocate using both heat inactivation and gamma irradiation. And there are some vendors of human serum which offer such dual treated human serum. If you can get that, if you need human serum and you can get that, I would definitely go in that direction, simply because it will mitigate the risk associated with parvovirus B19. I will interject that I had this real nice slide comparing actual data for a gamma irradiation study of human serum, and I compared the results obtained to what I would expect based on the bovine serum data. And it turns out that the expected results for the bovine serum and the actual results for the human serum for five or six viruses, we're very close. And just confirming my statement before that if you don't have specific data for human serum, go ahead and extrapolate based on the bovine serum data. And I think you'll be safe there. I think the next two slides are just some references. And again, you'll have these references if you want to look up this stuff yourself and become an expert on your own. So now I probably took a little bit more time than I planned, but we can address questions. Okay, very good. Again, you all have the slides. I hope it's useful to you. And if you have any questions that come up after the fact, you can address them to Robin and Catherine, and they will send them to me.